Okay, so as in the last video we have discussed about the electric field and electric field intensity. Alright, electric field was nothing but it was a region around the charge in which any other charge either feel the force of attraction or repulsion, and electric field intensity was basically the strength of the electric field. And electric field intensity, the formula of electric field intensity was force per unit charge, and the unit of that was Newton per coulomb, and another unit of electric field intensity was volt per meter, and volt per meter was also a unit for potential gradient. In today's video we are going to calculate the electric field intensity due to a isolated point charge. So let me write here the topic: calculating electric field intensity due to a isolated point charge. Due to a isolated point charge or source charge. Another name of point charge is source charge, right? So let me highlight this topic first with the yellow color. Today we are going to calculate the electric field intensity due to a isolated point charge. Okay, so for suppose if I have a charge here, Q, right? This is a source charge, and here I have a test charge or unit positive charge which is denoted by Q naught. Alright, here we know that the electric field force of line would be stronger. This is the distance between this, and here we know that between the point B and E it would be weaker. Alright, now we know that electric field intensity is equal to force per unit charge. We know that it is equal to force per unit charge, and this was the formula which we read in the when we were discussing about electric field intensity. Now we're going to calculate the electric field intensity due to a isolated point charge. We know that the electrostatic force, or you can say that is also known as Coulomb force. So let me write here: electrostatic force is equal to what? It is F is equal to K Q1 Q2 over R square. This was the electrostatic force, or you can say this is a Coulomb force. So F is equal to K Q1 Q2 over R square, that we have discussed in the Coulomb's law. Now as Q1 we have, source charge, so I can write here K only Q, and Q2 we have is a test charge or unit positive charge, so Q naught upon R square. Alright, this is the equation number 1. Wait, let me highlight this as well. Now doing nothing, however, putting the value of force, the value of F, or the value of Coulomb's force, or value of electrostatic force in equation 1. And what was equation number 1? No, this was equation number 1, right? This is equation number 2. Alright, so putting, or you can say putting equation number 2 in equation number 1. So let's put that, or wait, let me isolate this first. E is equal to force into we have charge, right? So 1 upon Q naught. So putting value of F, or putting equation number 2 in equation number 1. Putting equation number 2 in equation number 1, or value of F in equation number 1. So E is equal to K q naught over r square into 1 upon q naught. Q naught would be cancelled. Kq into 1 is kq over r square. Or we can write as 1 upon 4 pi epsilon naught, since we know that Coulomb's force or electrostatic force is equal to 1 upon 4 pi epsilon naught into q over r square. Alright, we can write as kq over r square or 1 upon 4 pi epsilon naught into q upon r square. Both would be absolutely right? So wait. Okay, so here we have got that electric field intensity is directly proportional to the charge, directly proportional, directly proportional to the charge. However, it is inversely proportional to the distance square or r square. Alright, so wait, let me highlight this as well. We have got that electric field intensity is directly proportional to the charge, however it is inversely proportional to the square of the distance. Square of the distance. Alright. So now imagine we have got here that we have calculated our electric field intensity due to an isolated point charge, right? Now for suppose if we have different charges, right? For the different charges, now I am calculating for the different charges. For the different charges, what would be for the different charges? Let us see that. So we know that there will be different forces as well. We know that E is equal to F upon Q, force per unit point charge or unit positive charge. Now the forces are different. Alright, forces are different. So F1 upon Q naught plus F2 upon Q naught plus F3 upon Q naught up to so on till Fn upon Q naught, because we don't know it, right? So we know that charges are same. So taking charges as common, 1 upon Q naught taking common, and F1 plus F2 plus F3 and so on up to Fn, right? So we know that this is the summation of the forces. So E is equal to 1 upon Q and till Fn, that is also known as summation of charges from F1 to Fn upon charge. So now finally I can write electric field intensity as summation of KQ n till the n, alright, upon r square. So this is what we have got due to different charges. Alright, so we have done nothing but we have calculated the electric field intensity due to a point charge, isolated point charge, where we got that E is equal to KQ over r square, means electric field intensity is directly proportional to the charge, however it is inversely proportional to the square of the distance. While we have calculated the electric field intensity for the different charges as well, E is equal to F upon Q, we know that forces are different, so F1 upon Q naught plus F2 upon Q naught, F3 upon Q naught up to so on till Fn upon Q naught. Then we know that charges are same, however forces are different. So we have taken charges as common, 1 upon Q naught as common, and in the bracket F1 plus F2 plus F3 up to so on till Fn. and we know that when we are adding these, we're going to use a function which is summation. So summation of forces till Fn upon Q naught, and that I can also write summation of KQN upon R square. So this is what we have calculated today for the different charges. In the next video, we're gonna study about the electric flux. What is that?